And hopefully the audio is working okay. Cool. Okay. So he gave me 4 problems to work. They're all conservation of momentum problems. So yeah. So if you have questions, just interrupt me. But they're all pretty similar to each other. So in this problem, we have this nozzle, and we got water flowing through it, and the cross section is decreasing as the water moves along. And so it gives us the pressure before the reduction in cross section and the velocity after, as well as just knowing that it's water at standard temperature. And then it wants to know what kind of force is inside of those bolts that's holding this all together and keeping it from like being pushed away. So for the givens, I'll just write these down real quick. So we know we have diameter 1 is 12 inches, and diameter 2 is 6 inches. We know that the pressure 1 is 38 pounds force per inch squared, or you could say PSI. And then we know that this second velocity is 56 feet per second. And we have water at 20 degrees Celsius. And then we want to know, we just want to know what's the force. I'm going to call it FB. What is the force in the bolts? And then we also know what the ambient pressure is. We know the ambient pressure is 15 pounds force per inch squared. And that's our, both of these pressures are absolute pressures. Okay. So, where I would start with this is to just write the F equals ma equation. And then in this case, that force is going to be horizontal, right? So we'll do X equals ma x, and then we can start looking at like, what do we know, what don't we know, that kind of thing. So if we write, well, I guess actually this is a little bit of a different way than he showed you in class, if I'm not mistaken. Because I think when he did this with you in class, he did the Reynolds transport theorem.
Yeah, he did.
Right. Okay. And then like, if it's steady, then the integral, the ddt integral goes to 0. And then you have like the m dot v out minus m dot v in term, that kind of thing. So yeah, so I believe when he did it in class, you had some sort of term over the control volume of, I think this is rho velocity So you have some sort of term that looks like this, plus, and then sigma m dot I v. This is out minus sigma m dot I vi in. But then if we're assuming that this is steady, then this would go to 0. And this is equal to sum of forces. So, yeah, so that's the way that he said he derived it in class for you. Another way you can think about it, if it's just easier to remember, this is not technically, I guess, this is a little bit just a way to remember it, not technically the way you would do it. But you could kind of think of MA as being M dv dt, derivative velocity. Hey, how are you? No, you're good. You're good. So we've got this like nozzle, and there's flow that's going through, and there's a cross section decrease, and we're looking for the force in the bolts. So I wrote the force summation in the x direction, and then I'm showing a trick on how to like remember, I guess, the equation you're using. So the original equation used was Reynolds transport equation that he derived in class, and that's that. So what you're going to end up with is sum of forces is m dot times delta v. But so I'm showing like an alternate way to kind of like remember that, I guess. But this is not technically the derivation of it. So, but you can think of MA as m times dv dt. And then if you think of that like m d over dt v, then you could say like dm dt times v, which is kind of like saying m dot. Basically, the units just work out. So when I was doing this, I was kind of like, okay, how can I think of MA as m dot v in my mind? So it points me back to Newton's second law. And so that's kind of the units, the way the units work out there, if that helps. But okay. So what we want, our fundamental equation that we're going to use is sum the forces in the x direction is equal to m dot delta v. Okay. I'll underline that.
Excuse.
Yeah.
Can you probably I missed it, but can you just explain why the first term where you have d dt, the integral of whatever, can you explain why that is 0, please?
Yeah, it's 0 because it's steady. We're assuming steady flow.
Okay.
Yeah. So if this was like a transient problem, then it would be a little bit different. Like if we were looking at a water hose and you turn on the water and you're wanting to know the, I guess, evolution of the water as it's approaching like a steady flow rate, that would be where you would have DDT is not 0. But if this is like if you turn on the water and you left it alone, and then after the water comes out and everything, and it's just like flowing, all not changing. This is that scenario.
Okay. Thank you.
Yeah, no problem. Okay, so okay, so then what we can do is we need to look at what our yeah. So now what we need to do is look at this picture and define the control volume. So what I'm going to do is Yeah, so if we look at this nozzle, then we know we're going to have a pressure. I'm going to change colors. It's easier to see. So we know we're going to have a pressure here. And we know we're going to have a pressure on that side. So maybe you can call those P1 and P2. And then there's going to be a force from the bolts that's holding this thing together. We'll call that, I call that FB. And then we know that there's an exiting velocity here, V2, and there's an entering velocity, V1. Okay, so all right. So when we write our summation, okay. Okay, so we write our summation of forces in the x direction equals m dot delta v. Then what that is going to give us is the force of the bolts in the negative direction. And then we're going to have a positive, you might say, pressure in the x direction for P1, and then P2 is going to be negative. So we can say P1 is positive minus P2, and that's equal to m dot V. I guess, yeah, this will be V2 let me do this. Okay, so V2 minus V1. So if we look at this picture, both of our velocities are traveling in the positive direction. So I think in the lecture, what he did is he said he had, I think, U's here, U2 and U1, and then he plugged in the V values. So maybe I'll do it like that, just to be consistent with what he was doing. So this is U2 and U1. But because V2 and V1 are both positive values, then this will be m dot V2 minus V1. Because what? I guess I'm saying that I'm defining x's that way. Yeah, and so I'm saying that they're moving in a positive direction. Yeah. So if you had flow going the other way, then that v value would be like negative v2. So which we'll see in the next problem. But okay, so then a good thing to pay attention to here is that P2 is atmospheric pressure, right? This pressure here is atmospheric. So the easiest way to work these problems is, instead of using absolute pressures, to use all gauge pressures. Because if you have gauge pressures, then you don't have to account for atmospheric pressure playing a role in this. So we can say that since P2 is atmospheric, since it's exiting the nozzle, that this will go to 0. So P2 is equal to, it says, what does it say? PA is 15 PSI. So then P2 gauge would be equal to 15 minus 15 PSI, or 0 PSI. So that's why the P2 goes to 0. And then P1 is going to be 38 psi. So then P1 gauge is 38 minus 15 psi. Which would be 23 psi. Yeah, so okay, so absolute pressure is like it is the, I guess, true pressure value. So you might say that's true pressure. And then gauge pressure is with respect to a baseline of atmospheric. So gauge pressure is saying at the atmospheric contributions assumed, and then we're adding on an extra amount of pressure, is what that's saying. So you could think of it like here we're, let's say, 30 feet above sea level. So you could say that, you know, if I held this pen up, that this is 36 feet above sea level. Or we could say that, let's do like a gauge height per se. And so this would be just 6 feet above, because we're saying 30 feet of the floor above sea level is just accounted for. So this would be 6 feet. Yeah.
Can you explain why P2 goes to 0 again?
Yeah, sure. Let me write this quick. So this is relative with respect to atmosphere. Yeah, okay. So yes, what I was saying is that we have these two pressures, right? On the left and the right. But P2 is, it's like where the flow is exiting the nozzle. And so P2 is equal to this P ambient, P atmosphere.
Okay.
Right. So if we turn P1 and P2 into gauge pressures, then since P2 is equal to your atmospheric pressure, then you just say that it's 0.
Okay.
Yeah. Because by definition, gauge pressure is how much more do you have than atmospheric pressure.
Okay.
But P2 is just equal to atmospheric pressure. So then it's 0.
Okay. Is it always like that case? Like wherever wherever the flow exits, the P2 is going to be just the atmospheric pressure?
Yeah. So if you have flow that's entering the ambient environment, then the pressure there is equal to atmospheric pressure. Yeah. The reason that P1 is not is because that's like a cut of the pipe. And so technically there's more pipe back over here. And then, you know, so that's right, exactly. Because you're still in the system at that point. So okay, so if we rewrote this, we could say that the force in the bolt, I'm kind of rearranging at the same time. So this is going to be P1 gauge plus m dot V1 minus V2. Okay. So I flipped around, I moved that right-hand side over, and then the negative I distributed and flipped the B's around. So, okay. So then, as we are looking at this, we know we have V2. It's given. we know that value. Actually, I wrote something slightly wrong there. This is a pressure. So to turn it into a force, we have to multiply by the area, right? So that should be P1 gauge times area 1. I just forgot to write that'll make the units work out correctly. So there should be an area there. And I'll write it here too. A1. That was going to be A2, but then we got rid of it. So we need to know V1. V1 is our unknown right now. So we need to know that. Okay. So we can do that by comparing the volumetric flow rates. So if we set the volumetric flow rate from the section 1 equals section 2, then we can solve for V1. Okay, so this is going to be V1A1 equals to V2A2. So then V1 is going to be equal to V2A2 over A1, which is going to be V2 was 56 feet per second. A2 was, well, the diameter of 2.2 was 6 inches. So here we might say, since we're working in feet, I'm going to put half a foot and just convert that in my head, 6 inches to half a foot. Squared times pi divided by 4 over, and then at section 1, we had a diameter of 12 inches. So that'd be 1 foot squared pi over 4. So I'm going to cancel the pi's and the 4's. And this will give a V1 value of 14 feet per second. Okay, so now if we want to go ahead and, oh cool, I have one more, sweet. So we know we have the force of the bolts is going to be P1A1 plus M dot V1 minus V2. So then P1 is 23 pounds force per inch squared. A1 is pi times 1. Well, here we have inches here. So I'm going to say 12 inches. The units messed me up when I worked this the first time. And so I'm trying to be careful about like making sure it's all right this time. But all right, let me have 4 and then plus M dot's going to be the density of water we can take to be 1.94 slugs per foot cubed times, I'm going to use 14 feet per second, which is the value at section 1. And then we have that same area. But again, now I'm using feet because this term is using feet as units. Would it help if I kept it consistent? Maybe. Okay. Oh.
Was that given the mass flow rate?
This thing,
Yeah.
that's density. Yeah, this is row VA for section 1. Yeah, this guy. Yeah. Yeah, so this whole term here is this guy. And then we multiply by 14 feet per second minus 56 feet per second. So then, when you calculate that whole thing out, what you will get is 1,705.337 pounds force. Yeah. And that's your answer. And maybe just a useful note here is that 1 pound force is equal to 1 slug foot per second squared. That always gets me thinking about the units of a pound force if you broke it up. So I'm going to note that for you. So yeah, probably not good practice to be mixing units like I did, inches and feet, inches in one term, feet in the other term. But I did it because they all cancel. So yeah.
And then the density, you can just find that from the table, right?
Yes. Yeah. So he just gave me the value, but that's like the standard value for density of water. Yeah.
But just like in case we forget, it's like on that table.
Yes, as far as I understand it is. I actually have it. Let me see if it's on this table here. Water. Well, this is metric, but it's that just in imperial units. Maybe it's on here. No. But yeah, I mean, this is 20 degrees Celsius just for metric.
Yeah.
Water, and so water. But yeah, whatever imperial version you have of that, it'd be just 1.94 on there. Okay. Do you have any questions about how I did that? Okay, cool. So this one's pretty similar. Problem number 2. So again, we have water at 20 Celsius. Again, this is atmosphere. So we're going to see that gauge pressure thing pop up again here. Atmosphere. Okay. So we know that the diameter of section 1 is 10 centimeters. We know the diameter at 2 is 3 centimeters or 0.03 meters. We know that we have a weight flow rate. This guy. Equal to 150 newtons per second. If I'm being honest, I have never heard of a weight flow rate before to this morning. Have you? Did he show you that in class? Weight flow rate? Okay. I didn't even know it was a thing until this morning. But a weight flow rate is a mass flow rate times gravity. That's all that is. So if you looked at units, you would get kilogram per second times times meter per second squared. Right. And so then this guy here is a Newton. So then you get Newtons per second. So I'm going to abbreviate as WFR, but I didn't know if there's some symbol he showed you in class for that I wasn't aware of. Okay, so then we know that we have a P1 of 2.3 atmospheres, and that is a gauge pressure. So we don't have to convert from absolute this time. It gives it as gauge. It says neglect the weights of water and elbow. So just to note that, make it simpler. And it wants, again, us to find the force in the bolts. I'm just going to say it's FB. Okay, so this problem is largely the same as the previous problem. So what I'll do is we're going to use the same formula, Fx, because, again, the only force that those bolts are going to have is horizontal, right? So it's going to resist motion. So we say this is FB, the bolt force. We know there's this pressure here, P1. And in this case, I'm not even going to write P2 because it gives us P1 as gauge. So then P2 would be 0 by default. Same thing. If you did have it, it's just like that. It's 0. Okay. So this is equal to m dot delta V. So if we go ahead and expand these terms, then we're going to get a negative FB if we're assuming that positive X is to the right. Then we'll have negative FB plus P1A1, since it's going to the right, that pressure. And that's going to be equal to m dot V, or I'll be consistent with how he does it, U2 minus U1. So maybe it's better if I write U here. And then we'll plug in the V's depending on what their direction is. So, okay. A point maybe that's good to make here is because this confused me about an hour ago when I asked him about it, is that when you're looking at a pipe system, so like whether it's like this or if it was like this, let's say, however it is, the pressure always acts in. Right. Okay. So, because I was in my head, I was going, okay, is the pressure going to be like fighting the motion or assisting the motion? Like, how does that work? But the pressure is always going to act in at your control surfaces. And then the direction of the flow is important. Like if it's flowing this way or if it's going that way, that is important. But where that gets captured is in the m dot U2 minus U1 term. So the negative direction of flow will get captured in that term over there. I wouldn't think of it as shear stress. That is the oh yeah. I mean, I guess if you're looking at the microscopic level, then yeah. I mean, depending on how that's flowing, you're going to end up with like a yeah. I mean, you're going to end up with like a profile that's either this way or this way. Yeah. So you could think of it too, just relatively, like when you have F equals ma, you know, the direction of the acceleration matters, right? And so this is kind of like you're capturing the direction of the motion in the V term, but the pressures will always act inwards. So yeah, that's just a side note because I was wondering about some of the signage a little while ago. Okay. So then we rearrange this, we'll get FB is equal to P1A1 minus M dot U2 minus U1. Okay. Now we can plug in our V's. So in this case, velocity 1 is flowing this way, right? So it's positive. So I'll say velocity 1 is going to go here as a positive value. And then velocity 2 is going to be going opposite that. So it's negative. This would be negative V2. So then this is FB equals to P1A1 minus M dot negative V2 minus V1. All right, so we know what P1 is. We can solve for A1. And then the velocities are two unknowns right now, right? So we need to know what are these. So we will solve for those by using our volumetric flow rate. We know what the weight flow rate is. And if we divide weight flow rate by specific weight, that's going to give us Q. Because you could think of this as, like I said, M dot G. And this is rho G. So this is rho velocity area G over rho G. So then that's Q. Okay, so then if we say Q1, or Q will be consistent, it doesn't matter. Q1 is equal to Q2. So Q is going to be 150 newtons per second divided by 9,790 newtons per meter cubed. And that's going to be 0.0153 meters cubed per second. So then V1 is going to be Q over A1. The diameter of the A1 cross section is 10 centimeters. That's going to give 1.95 meters per second. And V2 is going to be very similar. I think it was 3 centimeters, or 0.03 meters squared over 4. And that's going to give you 21.6. Okay. So now, if we plug all that in, then what we're going to get is FB equals 2.3 atmospheres times pi. This is the cross-section area for section 1. And then we'll note that atmospheres is not standard units. So we can say that we want that in pascals. So we'll say that there's 101,350 pascals in an atmosphere. Cancel those. And then we'll say that if we need our mass flow rate, so our weight flow rate divided by gravity. I'll do it this way. This is the way I did it before. Volumetric flow rate times rho. That's the way it's most commonly seen. So that's going to be our m dot, and that's going to be multiplied by our velocities. So we know we have a how did I write it? Yeah. So we know that we have a negative here from this equation. There's a negative right here. So then we have negative V2. So V2, the horizontal component is going to be cosine of 40 degrees times that. So this is V2 cosine 40 degrees minus V1, which was 1.95. Meters per second. And then our m dot, if you calculate that value there, it is 15.27 kilograms per second. So then when you crunch those numbers, you're going to find the force in your bolts is 2,112.8 newtons. Oh, I wrote V2 here, 21.6. Does that make sense?
So all of this is like the force on the water.
Let me see. Let me understand. I just want to make sure I understand what you're saying. So you're saying that this, where is this FB force?
Yeah.
So FB is the this is kind of what I was getting at when I was talking about the pressure directions, right? So the pressure, right, right. Yeah. So if you think about the control volume here, right? So we're kind of saying we have like this like control volume, and the bolt, what it's doing is that pressure is going to constantly be like putting like stress on the whole system, trying to like make it move. And so the bolt there is resisting the pressure, like ripping the system apart. So if we had assumed that force to be in this direction, let's say, we would have gotten a negative value. And that negative value would have told us that this assumption was wrong. And it's actually going to the left. Does that answer? Is that kind of what you're getting at? It help me understand what you were saying there. Oh, okay, yeah.
I understood that, right? I was just, is it the water hitting as soon as the wall curves?
Oh, I see what you're saying. So you're saying why does the pressure generate a force? You're saying, is it the water like running into that curve? Is that what's generating the force? Okay, that's what you're saying. So I'll ask him about the physical representation of how that is hitting. Yeah, me. Force of P because, yeah. So tell me if this helps. I don't know if this will help at all. This is how I'm thinking about it. So when you talk about pressure and we say that like the pressure's acting in right here, yeah. So if we had a pipe and we're saying that the pressure is acting in here and in here, you know, the pressure there is kind of actually omnidirectional. It's, yeah. So it's like the pressure is kind of like doing this. It's trying to like rip the whole thing apart. So that's what was getting me earlier is I was thinking about, okay, is pressure going to be assisting the force or is it going to be resisting the force? When really it's pushing in at, at that surface. But as far as like, is it the flow going around there that's causing that force? I'll just ask him. I'll get back to you. Yeah. Okay. Is there anything else with that? No. Cool. So for this problem, now we have a vertical plate, and yeah, now we have a vertical plate. It has a hole right there in the middle of it. We have a stream of water running into it and like fanning out with a smaller hole, or the hole is smaller than the jet of water. And so part of that jet gets through the hole. So we have, for our givens, we have a jet. The jet of water has a diameter, I'll say subscript J, of 6 centimeters. We know we have water at 20 Celsius in case you need to use your table to find like a density value. And then we know that the diameter of the hole, I'll say that's H subscript, is 4 centimeters. And then I don't know why, but for some reason the problem statement didn't make it on this problem. So I'm just gonna have to tell you verbally and kind of write this down what the rest of the statement is there. So essentially what we're looking for is it wants you to find this force. I'll say it's F plate, FP. What's the force holding the plate steady? Force holding plate steady. Okay. And we know the velocity v1. I'm going to call this section 1, call this section 2, and it does as well in the figure. So v1 equals v2, which is 25 meters per second. And there's two assumptions that we have here that are not stated. They would have been later in the problem statement. We have symmetry of flow. So what I mean by that is this guy, those two flows are equal to each other. So what that means is that if you sum forces in the y direction, it's going to be 0. That's what that's saying. If for some reason like they were not symmetrical, then you'd have a some sort of force in the y direction. And then we also know is that this is steady. So we've only done steady so far. Steady flow, which means the d over dt term equals 0. Okay. So for our solution, yeah, so this is very much the same as before. We're going to sum the forces in the x direction, so equal to m dot delta u. I'll call it delta u there. And then we know that we're going to have this negative FP force. We also so that's our only force there. We don't have any pressures because this is like an open system, right? There's no like pipe or anything. So over here we have atmospheric pressure, and over here we have atmospheric pressure. So there aren't any pressure force terms like before. So this is going to be equal to m dot. Now the weird thing here is that you can't assume m dot's the same. Yeah.
So even though it says the water jet, so we still can assume that the left side is atmosphere.
Yeah, and the reason for that is because even though it is a water jet, it's exposed to. There's nothing like containing it. Yeah, there's nothing containing it inside. So yeah. Yeah, because we're not thinking about the pressure in the jet, like in there. This pressure that's impacting the outside of the jet is atmospheric pressure. So then the pressure that's here, or yeah, the reason is because there's nothing like there's no pipe containing it, and so then we end up with just that force term. So yeah, so the weird thing with this problem is that you can't assume a consistent mass flow rate, right? Because the mass flow that's here, some of it is like going up this way, some of it's going this way, and some of it's going through. So the mass is literally splitting into like different portions. So I'm going to say this is mass flow jet times the velocity of the jet. Okay. And then let me write it like, okay. So this guy here is m dot u2 minus u1. So then if we say that this u2 term is going to be a combination of the flow going up plus the flow going down plus the flow that's going through the hole because of that incoming jet splitting into 3 different directions. So these are our 3 directions here. Then U1, that is the flow of the jet itself. So then when we write this, we can say that we have m dot up, U up, plus m dot down, U down, plus m dot hole, U hole, and then minus, there's that minus sign, m dot j, uj. Okay. And then I guess I also have to make sure that these are x. These are x direction velocities, just to be explicit about that. So because they're x direction velocities, and the upward and downward flows are purely in the y direction, then these go to 0. Right. So then if we rewrite this, switched around, then we have P is going to be m dot j uj minus, oh, it always does this, minus m dot hole u hole. Oh, okay. Yep, so we can just say that the force is equal to, so m dot j, I'll rewrite it, m dot j uj minus m dot hole u hole. And I'll wrap this up like super quick, that way you don't have to stay. But so this will be 998 kilogram per meter cubed multiplied by the velocity, 25 meters per second, multiplied by, again, the velocity, 25 meters per second, times the first area, which is going to be pi times 6 centimeters. And then we have minus 998 kilogram per meter cubed times, again, we have 25 meters per second and another 25 meters per second. And then we have this area is pi 0.04 meters squared over 4. And when you calculate that, it's 973 newtons. The reason for the 2 velocities is because m dot u is rho va times v. So in this scenario, both of our velocities are going to the right, so they're both positive. So when so uj became a positive v1, was a positive v2. Do what?
That makes sense.
Yeah, because they're both going to the right. So then you plug in positive V1, positive V2. And then, so this, one of those is for the mass flow rate calculation, and the other one is what that U became the other velocity. So that's why there's two of those. So yeah, do you have any questions about that? Any questions online about any of this? Okay, cool. Then I'll go ahead and shut it down. All right. If you have any questions online, just let me know. But I'm gonna go ahead and turn this off. Thanks for being here.